These are the notes for day 50. We're going to spend one day on inverse trig integration. There are two slides. The second slide is really just a review. So inverse trig is primarily contained on just this slide. So as I mentioned when we're looking at derivatives, arcsine and arccosine both have derivatives that are the same, that are just off by a -1. Same thing with arctangent and arcotangent, and then arcsecant and arccosecant. So that means that we only need to look for 3 and not 6 different patterns. If there happens to be a negative here, you can move it out front, and then you're still going to get the antiderivative of this statement here is arcsine u over a. So if you paid attention to what we did with the derivatives of arcsines, and if you paid attention to the chain rule, this hopefully will make a little bit of sense. I'm not going to prove them. You could use the same triangle arguments that we used to derive the derivatives of these to wind up with this pattern. But if you see the antiderivative of du over the square root of a constant squared minus u squared, that's arcsine. If you see the antiderivative of du over a constant squared plus u squared without a square root, just a squared plus u squared, that's arctangent. And then the antiderivative of du with a variable and then variable squared minus constant squared is this. The 1 over a's in the front come from the chain rule, and then the absolute value is, again, that thing that's a little bit mysterious depending on how you define arcsecant. So first one, this is already set up nice and neat. We have x plus 3 squared, so that's going to be our u. Our u will be x plus 3. 12 isn't a great squared number, but if you take the square root, we can work with the square root of 12. So replacing 12 with a squared, where a is defined as root 12, replacing x plus 3 with u, where u is x plus 3, we get u squared, and the antiderivative of this is inverse tangent. So I took this statement, wrote down the formula, and then substituted in for a and u and got that answer. Okay, you could simplify root 12 into 2 root 3. Sometimes the back of the book does, sometimes it doesn't. Second one. This polynomial isn't set up like any of these denominators up here, so we're going to use an old trick of completing the square. If I take the first two terms and then separate the constant away from those two, completing the square, you take the linear term, cut it in half and square it. So -6 divided by 2 is -3. -3 squared is plus 9. If I add a 9 to these two things here, this factor is nice and neat. But to offset the positive 9 that I put here, I'm going to subtract the 9 over here. 13 minus 9 is 4. And we wind up with completing the square in this version. Generally, it's written constant squared plus variable squared. So I just changed x minus 3 squared plus 4 into 4 plus x minus 3 squared. So now this matches the inverse tangent setup. A is 2, u is x minus 3, du is a single dx. So everything works out nice and neat. I write down the result and substitute in. A is 2, u is x minus 3, and there's our answer. Okay. The third one is demonstrating something that's a little bit more complicated. First issue is I have two terms up here, which using your fraction rules, you can take two terms divided by a monomial and split them into a over c plus b over c. So I took x to the fourth and divided it by the numerator, and then I took 4 and divided it by the numerator. That way I can do two different u substitutions on these two different antiderivatives. If I look at the first one, x cubed is 1 degree smaller than x to the fourth, so a good u to use would be x to the fourth minus 4, which du is 4x cubed. I don't have a 4, so I'll throw a 4 in there and offset it with a 1/4, and now it's a pretty straightforward u to the -1/2, because my u was this in the denominator, so the square root is 1/2, and in the denominator is -1/2. Antiderivative becomes u to the 1/2, reciprocate the exponent 2, multiply those two together, and you get this statement here. The second one's a little bit more complicated because I have this x here and I don't have an x to the third up here, but this quantity here is starting to look like the inverse secant. So I'm going to let u equal x squared, du is going to equal 2x dx, and that doesn't quite work out great yet, so I'm going to solve for dx. dx is du over 2x. So if I take and replace I'm going to move the 4 to the outside, which I put here. The dx is going to become du over 2x. The x is still there, and I did replace my x to the fourth minus 4 with this underneath the square root. So I've got du and u statements, but now I've got to work with this. Well, if I take u, which is x squared, and take this x times 2x and turn the x squared into a u and bring the 2 outside, now I have a 2 out there. The 2 that I just brought to the outside is actually in the denominator, so 4 divided by 2 is 2. Okay, now this is set up like this statement here. I've got the antiderivative of du over u squared minus a squared. So I need the arcsecant formula. So 2 was on the outside, 1/2, because a was 2, inverse secant of the absolute value of x squared over 2 plus c. Absolute value of x squared, I don't need the absolute value of ours because x squared is positive. 2 times 1/2 is 1. So here's our final answer right there. Okay? So the second slide here is in the inverse trig integration section, but it's actually a review of related rates, and we're going to be using derivatives more than antiderivatives. So 2 questions. On a morning of a day when the sun will pass directly overhead, an 80-foot building on level ground is casting a shadow onto the ground. So here's my 80-foot building. The sun is here, casting a shadow onto level ground. At the moment in question, the length of the shadow is decreasing by 2 feet per minute. So I took an arrow and said that my x value is changing at 2 feet per minute, and since it's decreasing, I made dx dt -2. Find the rate of the angle between the ground and the sun is changing when the shadow is 60 feet long. So find d theta dt given x equals 60. And anytime you're given a value, you plug that in at the end. You want your x to carry along so that you can take derivatives and then substitute at the end. So if I look at my right triangle, it would seem natural to say the tangent of theta is 80 over x, okay? Which means if I solve for theta, theta is the inverse tangent of 80 over x. If I'm going to be taking derivatives, this is a bit of a mess because of the x in the denominator. So I'm going to abandon that thought and switch to cotangent. Cotangent of theta is adjacent over opposite, so x over 80. Theta is the inverse cotangent of x over 80, which means now when I go to use the chain rule, I'll just get 1 over 80 instead of a more complicated x statement. So dx dt is d theta dx times dx dt. I just said that wrong. D theta dt is d theta dx times dx dt. D theta dx, I can just take this statement here, take the derivative. Dx dt, I was told that that is -2. So the derivative of inverse cotangent is -1 over 80, 1 plus x squared over 80 squared, okay, times dx dt, which eventually be -2. Multiply top and bottom by 80 squared, so I get -80 over 80 squared plus x squared. That gets rid of that second denominator down there. And then my final answer is -80 divided by x is replaced with 60 finally. Dx dt is replaced with -2, and I get 0.016 radians per second. The rate the angle between the ground and the sun is changing is 0.016 radians per second. Second problem is 20-foot billboard is attached to the side of a building. The bottom of the billboard is 70 feet above the viewer's eye. So here's a 20-foot billboard, and it's 70 feet off the ground. How far from the building should the viewer stand to get the best view of the billboard? Maximize the angle between the line of sight and the top and bottom of the billboard. So we'd like to maximize this angle theta, but the problem with theta is that it is not part of a right triangle. So we're going to use 2 other angles that are parts of right triangles. Alpha is the angle in the small right triangle. Beta is the angle in the big right triangle. Theta here is the difference between the big beta angle and the smaller alpha angle. So theta plus alpha is beta. The one that we're interested in, theta is beta minus alpha. And again, both beta and alpha are part of right triangles, so now we can use our right triangle statements. Again, I could use tangent. The tangent of alpha is opposite over adjacent, 70 over x, but that's not so good for taking derivatives, so I'm going to use cotangent. Cotangent of alpha is the reciprocal x over 70. Cotangent of beta is x over 90. Solving for alpha and beta, alpha is the inverse cotangent of x over 70, beta is the inverse cotangent of x over 90. So theta, which was beta minus alpha, is this inverse cotangent minus that inverse cotangent. I'm going to take the derivative using the inverse trig function derivative rules. I get this minus that. And then I had to skip a little bit of the algebra because I ran out of space. But if you multiply through by 90 squared to get rid of this denominator and 70 squared to get rid of this denominator, and if you put the positive term first, you should wind up with something that looks like this. So again, negative times negative is positive. So I put this first, multiply top and bottom by 70 squared. Put this second, multiply top and bottom by 90, and I got this. Now to get critical numbers, set it equal to 0, which means 90 is going to come over the other side. Do a little bit of cross multiplying and collecting of like terms. You get 90 squared minus 70 squared equals 70 times 90 minus 90 times 70 squared. X squared winds up equaling 6,300, so x is roughly 79.5 79.372. I put that on the number line, said 0 and 80 would be good numbers to test. I plugged those into theta prime right here, and obviously I used my calculator. Found out that this was positive and this is negative, so that tells me that my function is increasing and then decreasing. My theta function is increasing and decreasing. So 79.372 is the maximum angle when x is 79.372. I said that backwards, but x is 79.372, and that produces a theta max. Okay, that's it for day 50.